So last time we did, we finished heapification. So that was this figure basically. You are given this green array and then you try to check bottom up where the heap axiom is failing. And wherever it is failing, you correct it by replacing that node by min of the child, min of the children. One of the two children is min. And we of course assume distinct entries. In this case, the integers are distinct. So this travels to the root, this process, and this one subroutine we have written in detail, which is the heapify. This corrects at I, so that I and below the subtree becomes a heap. And there will be an outer program which will call this heapify at the bottommost, and ultimately this heapify has to be called on every element, right? Because if you miss any element, then it may not be a heap. So ultimately it will be called on all the i's, but in what order, that is given by decreasing height. Well, or actually here it is increasing height and decreasing I. So in that order you go over every element in the array, and that we have analyzed by this sum sigma nh times time of heapify. It comes out to order n, and based on that you can now do heap sort algorithm. Okay, so heap sort is given an arbitrary array, make it a heap, heapify it, and extract the min. So you will get an ascending. You will have the sorting algorithm that sorts arbitrary array of integers in increasing order. Any questions? This is also an n log n algorithm for sorting. Something that we will not do in this course is a much better heap than the heap that you just saw. So with much more work, so what we just did is called a binary heap. This is the basic binary heap. This can be drastically improved, almost made optimal. Which will then be called the Fibonacci heap. So this is not in the syllabus. Okay, but if you are interested, you can read about this. So the advantage of this optimal heap, the Fibonacci heap, is that almost every operation is constant time. So this is the comparison table. So min operation, insert operation, extract min, decrease key, and merge. Okay, so these are the operations that we were interested in the mathematical modeling. So in what we have achieved in binary heap is you can report the min in how much time? O1 here, right? Because it's just the root, the first element in the array. Insertion in log n, the height of the heap, the height of the tree. So insertion, extract min, decrease key, all in log n, and merge in. Yeah, for merge you have to see all the elements. So trivial was n log n, and this is the previous analysis gives you order n. Now this picture is very different in the case of Fibonacci heap. So it is min is constant, insertion is also constant time. Decrease key is also constant time, and merge is also constant time. Okay, so 4 out of 5 operations will be constant time. Can extract min also be in constant time? So suppose extract min, you have a heap data structure where everything is constant time. What would it mean for sorting? Sorry? Right, so then you can sort an arbitrary array in linear time. Okay, that is an open question. That is not known how to do. So this will not be constant time, this will be slightly more. So this is log n time. Okay, so Fibonacci heap has everything constant except extract min, which again gets you sorting in n log n. Okay, so we can't really improve sorting. Till now it's an open question. So because of that you have this okay, so this still gives, it will not improve sorting algorithm, but everything else it improves. So Fibonacci heap is works differently. It will not just only use this complete binary tree, but it will actually use linked list also. It will have pointers, so that merge, especially merge, is constant time. You don't have to look at every element to merge. So it's a different construction altogether. We will not do this in this course. So one exercise you can do is compare the 3 sorting algorithms. So which is merge sort, quick sort, and this latest that you have seen, heap sort. Okay, so study their importance in practice. In practice, which one will you use? For different problems, quick sort may be better than merge sort, although theoretically or asymptotically they are all the same in the worst case. Any questions till now? So the next thing we will do is more clever data structures, which are called augmented data structures, augmented tree data structures. Will not, of course, do all of them, but just some examples related to interesting problems. So we'll study more tree-based data structures, which are loosely inspired from heap. or before that BST. So they will not quite have this heap axiom or BST axiom, but they will still have a similar picture. And they will have more properties depending on the problem. Okay, so these are called augmented tree data structures. So first problem that we want to solve by this augmented style data structure is, it's a very useful problem in practice, or at least its variants are very useful. So this is called multi-increment well, let us just stop here. So this is the problem of multi-incrementing an array. So what is given, what you have to do here is you are given a list of integers, say an array. You want to maintain a data structure of n integers. So x0, so just think of this as a list. The problem is to design a data structure which at all times will store n integers, and the operations you want is report the ith element. So they are in the indexed. So what is the value of xi? That should be very fast to report. And second thing is this multi-increment operation, which is xi to xj, all of them you want to increment in the same way. So you are given I, j and delta. So xi to xj, every element you want to increment by delta, right? So trivial thing will be you just do it one by one, but we want something better. So this is the list of integers x such that the two operations are efficient, as efficient as possible simultaneously. So first is report I. Which just outputs xi, and second is multi-increment I, j, delta. So you want to add delta to each xk, k I to j. Okay, so you can maintain this as an array. So that will solve, that will report xi very fast, just constant time. But the problem will be that this multi-increment, you have to increment I to j by a for loop, right, which is linear time. So that is the brute force idea. So array X requires j minus I time, which is which could be around n. Okay, because if I and j are, let's say, n by 2, you are around the midpoint, n by 4 on one side, n by 4 on the other side, then the interval length is n by 2. So usually this will be the case, and you want to handle a lot, you want to handle many queries in a day, right? So most of the queries will be of this type, where j minus I is as big as n, multiple of n. So this multi-increment function will be very slow. So the question is, can you do it faster? So in fact, when you want to do this faster, then obviously reporting will become slower, because you will not be working with an array. So you cannot report xi in constant time. So you want to do, essentially there is a trade-off. You want to do this number 2 faster at the cost of 1. So for example, by your tree intuition, can you do both of these things in log n time? Right? So reporting becomes a bit slower, but multi-increment becomes exponentially faster. That is what we'll solve. Yes. Yes, so this kind of problems we have seen, like min range, and there was other, there was another problem where you needed to take prefix sum. But they were all working with at least linear time, n or n log n and so on. So you have not yet seen an idea which can solve this problem, both the operations 1 and 2 in log n time. Only way to do this is using a kind of a low height balanced tree. But then the problem in even, I mean, if you just store these values in a tree directly, like a red black tree, going from xi to xj will still take n time or more, simply because there are too many elements, right? So how can you increment all these elements without looking at them? Any ideas? So this problem, or this solution at least, is used every day by you in Google Maps. Okay, so Google Maps also uses a similar augmented tree data structure. So we'll discuss this once we have finished the solution. So the idea here is use the collaboration of intervals. So this collaboration vague trick of collaboration we had also used in min range problem in the first month of the course. So collaboration means that we'll first of all look at intervals. So I comma j is an interval, right, which overlaps with the I plus 1 j interval, which overlaps with j minus 1 j plus 2 intervals. So all these intervals, although they are so many, they are n square many intervals, but they overlap a lot. So you want to use that collaboration in a tree structure, so that when an interval is queried I comma j, you can immediately go to that. So you want to work with intervals, so you push intervals in a tree. Okay, so arrange the intervals as BST. So instead of elements, instead of the integers, we will think of intervals. and for an interval you can then increment. So increment delta is something that is acting on an interval. Okay, you do that abstraction. Don't think of element by element, but the whole interval is being incremented. So if you are storing intervals in a tree data structure, then when I comma j delta query comes, you can just insert delta in that interval location. Okay, so this is more abstract than just a single integer. So it will need many examples to make you understand. So what you can do is, let's take a small example here. So think of the 0-5 interval. We want to get to all the intervals by drawing a tree under this, with this as root. Okay, so with the binary tree intuition, what should you do? What should you put on the left child of this? 0, yeah, so maybe this should be 4. So put 0, 2 here and 3, 4 here. And what should be the children of these? So these are just the singleton intervals, right? 0, or no, not yet. So this is 0, 1, 1, 2. It's not very good. Wait. Yeah, I think I need powers of 2. So that is another thing. I'll need the length of the interval for this to be power of 2. So let me take 7. Okay, so this interval is of size 8. So for intervals which are powers of 2, I will give you how the complete tree is, binary tree is drawn. So now what should it be? So there are 8 elements you divide into 4 and 4, right? So first is 0 to 3, next is 4 to 7. So now 0 to 3 are 4 elements you divide into 2 parts. So that is 0, 1 and 2, 3. And here similarly 4, 5, 6, 7. And now I don't have space, but below this also there is a leaf layer where the leaves are singleton 0, singleton 1, then singleton 2, singleton 3 and so on. Okay, so this will be the complete tree where any interval can be partitioned into union of the leaves. In fact, union of very few of these nodes. So for example, how should you partition 0 to 4? In the most efficient way possible, coming from the root. So you should maximize with using 0, 3, right? And then the rest goes in the leaf. Okay, so we can use this. So on the left of the root, you should try to, so anywhere you go, you should try to maximize. So to cover 0 to 4, the maximum you can do is just go to the child of the root, which is 0, 3. And then you see that 4 is still remaining. So for which you can traverse the right subtree and then you have to go to the leaf. The leaf will be exactly enough. So the distances that you have to travel here depend on the height of the tree. Okay, so 0, 4 is partitioned like this. How will you partition 2, 5? So to get the lower part, 0, 3 is incorrect because it has extra elements. It has 0 and 1. So you have to go to the right side of that, which is 2, 3. So 2, 3 will work. And what next? 4 and 5 remain. Right? So you have to go to the right subtree of the root and do what? Again, 4, 7 is not enough, so you have to go to the left child, so you get 4, 5. So, in this way, you can write any interval I, j as a union, disjoint union of how many intervals? Maximum it will be log of 8. Okay, so log n intervals. So what this example tells you is that if I have 0 to n minus 1, so let us assume first of all n is a power of 2. And what this traversal of that tree of intervals, it's called an interval tree, gives you is the root which represents the whole set 0 to n minus 1 requires how many intervals? What was the number of nodes in this tree? I mean, we did not draw the leaves, but including the leaves it is 15. Right? So 0 to n minus 1 requires 2n minus 1 intervals in this interval tree. And any I, j using this logic, using this trick can be intervals, minimum number of intervals. Can be written as order log n many nodes or many nodal intervals of the interval tree. Is this clear? So this log n is coming simply because of the height of this tree. Right? The height of this tree is log n because this is a complete binary tree. We are taking n to be power of 2, so it is really complete. It has all the nodes. Its size is 2 raised to L plus 1 minus 1. So for 8, which is L equal to 3, you are getting 15 here. 7 I have drawn and 8 more in the leaves. So 7 plus 8. Okay, so there are these many nodes in the interval tree. uh, height is log n of the tree. So in this case, you have 4 layers. There is the leaf which is at height 0, and above that you have 3 more. And that is what determines the search for these parts of an interval. Right? So that is order log n only. So you should prove this. And BST search. Okay, so complexity of the search algorithm in BST and height of this tree will give you the result. So that is the important augmentation that we have done. And right now we haven't even looked at the integers in the array. Right? This is simply for the indices 0 to n minus 1. The integers now we have to put somewhere. So we should put it where? Where should you store the actual integers? Sorry, leaves. Yeah, so in the leaves we will put the integers of the array. Okay, and above that there will be this augmented structure, tree structure of the interval tree for the indices. So that is what we'll do next. So the plan is put x in the leaf, to get a complete binary tree. Okay, as we had in the heap case. In the heap case, we were looking at a complete binary tree which may not be fully complete, but still the all the elements in the leaves were arranged on the left side. Okay, so in the same sense, you maintain this skeletal structure of complete binary tree, and the augmentation is that the internal nodes above the leaves are seen as intervals. Right, that's the augmentation. And then you do multi-increment. Ij delta by putting plus delta in the internal nodes which you are using to get to the I comma j interval. Okay, so you have to put delta in the right places. So in the relevant nodal intervals or internal nodes, I can just say now. Okay, so how exactly will this be done? We will see shortly. Is the plan clear? So what are these relevant internal nodes? And how will you put delta there, and then how will you do the reporting? So those pseudocodes we will see in detail. But let us first do this in an example. So the augmented data structure looks like this. So the array values are stored here. So the array is let's say 4, 14, 9, 17, 23, 29 and 91. Okay, so these are the 8 values in the array. These are the integers. So these are the records or the keys which your data structure contains. Everything else is abstract. And here it's this augmented tree data structure where the nodes, the internal nodes, these 7, 1 plus 2 plus 4, will be seen as storing the interval. Well, not storing, but they are indexed by an interval, right, which was drawn earlier. So the root is basically 0, 7. I will not write it again because it will become confusing with the values, because I also have to put increments in these bubbles next. But you just use the mapping from that. So 0, 7 is the root, then the first two are 0, 3, 4, 7 and so on. And what was missing in that are these red integers, which I have added now. Okay, so this is the augmented data structure that we maintain. Now, to begin with, the increments we are assuming to be 0. Okay, so in this data structure, the increments will be slowly added as the queries are made, as multi-increment function is called. So let's say to begin with they are 0, and the array is in the leaves. And then what happens is multi-increment is called on interval 0 to 6. You have to add 10. Okay. So what should you do? How will this data structure change? Yes, but not all of them, right? We'll not add 10 everywhere. If you add 10 in the root and then in the child, then it becomes 20, 10 plus 10. So we have to add 10. This is why I said that the relevant internal nodes has to be carefully found. So we'll add 10 in the lowest possible place and then not above. Because if you add 10 in the third layer and also the second layer, let's say 10 and the parent is also 10, then intuitively it adds up to 10 plus 10. You don't want that. So this is what will happen. So first of all, how do you decompose 0 to 6? Did we do that before? Yeah, so first you have to decompose that, right? How do you write 0, 6? Yeah, so this is a bit longer. So 0 to 6 has to be partitioned in under 3 or less intervals. So let's recall the indexing mechanism. So in 0 to 7 is the root. 0 to 6 means that you take 0 to 3, then you take 4 to 5, and then you take 6. Okay, which translates to what locations in this picture? So 0 to 3 is here. Where is 4 to 5? So that was this one, and 6 is this one. Right, and I mean we'll give the pseudocode, but you can see how we found 0, 3, 4, 5, 6 is by doing a search in this tree, right? So we went left from the root so that we hit 0, 3, and then 4, 5 we went right and then a left, and for 6 we went right, right and left. So so what is the interpretation of this? With vis-a-vis 10, where should we do a plus 10? This whole space of the array indices are basically now divided. So we have kind of this part till here where uniformly 10 has to be added, and then we have this subtree where uniformly 10 has to be added, and this third part where 10 has to be added. Right, so when you divide the interval into internal nodes, the internal nodes give you subtrees which divide your array into zones where you want to uniformly add 10, right? So let me just do that now directly in the tree to give you the result. So you will do, we want to do a 10 here, 10 here, and we want to add 10 to these places. So I'm adding 10 to 4, then 10 to 14, then 9 and 17 I will not touch, 23 and 21 also not, 10 to 29 and 91 is unchanged. Okay, and the remaining values I don't touch. So this is what we'll get. Yeah, so this is why I gave this example, because intuitively you can write it there, but my pseudocode will do this. The pseudocode is general. What the pseudocode will do is it will first increment. So this is your x0 and this is your x6. So the pseudocode increments x0 and x6 first. So it adds 10 to both of them, and after that it makes other decisions. So I mean the way the pseudocode is, because it will help in other more complicated examples, it will be better to do this. So then what, so maybe I can write the pseudocode ideas first before giving the code. So these are the steps we are following in the pseudocode. So increment the leaves, xi and xj by delta. That's the first step. And then after that you check whether the leaf xi is the left child of its parent. If it is the left child, then the sibling is also incremented. So I'm adding 10 to 14. And you check whether xj is the right child. If it is the right child, then the sibling will be incremented. in our case, it is not a right child, so there is no, we don't increment the sibling. Everything else we will do in the internal node. Okay, that's how the pseudocode will be written. So if this U and V have different parents, well, if U and V have the same parent, let's say we were talking about just 4 and 14, right, then already we are done. If Xi and if U and V have the same parent, for example 4 and 14, which is the 0, 1 case, then we are already done. But if they have different parents, then it means that they are further apart. So then the following steps will be done, which is, as I just said, so if U is a left child, then increment U sibling. And if V is right child, then increment V sibling. And once the siblings are incremented or not, then you move to the parent. So you move one level up. So which means that U you set to parent of U, and V you set to parent of V. So this is moving up. And that's it. Okay, that's the pseudocode. So I want to use this simple pseudocode, and this is what I've executed on this example. Yes. So you want to add 10 in the internal node. Yeah, but you have to give a consistent pseudocode. It will not work in all cases. No, so what you have to check in general is that whether U is a left child or a right child. If U, like this Xi, the first thing that you want to increment, if this is a left child, then its sibling is on the right, so that also will be incremented. But if U is a right child, then its sibling should not be incremented. So whether the parent of U you can put delta or not depends on which direction U is. So that check has to be done. So you can change the pseudocode, but then it will change it will not become shorter. So this check is the minimum that you have to do. 3 checks are there. So parents of UV are different. U is a left child and V is a right child. These 3 checks you cannot remove. So I have given you the shortest pseudocode, and for this the execution is as follows on the example. That the 4 and 29 you immediately increment. Then for 4 sibling is 14, you increment that. And then you see what remains in the middle. So what remains is 9, 17, 23, 21. So their internal node, the parents, you increment them to 10. Okay, that completes the multi-increment for 0 to 6. What happens in the stopping condition is that when you reach the parents of this 10 and 10 internal node, that is 0 and 0, so you will reach here. So you reach here and you reach here. You reach these 2 dots, and then the parent is the same, so you halt. That's the stopping condition. Okay? So you start from Xi, Xj, increment them, and then move up till you reach siblings. At siblings you stop. You halt the sub pseudocode. So I think our time is up. This has to be written as a pseudocode now. Any questions? It's actually quite easy to write this as a pseudocode. The only complication you have to work out is how is this data structure stored on the computer. So again, as I said, use the heap idea, store it as an array. So the array size will be, for the whole augmented DS, the size of the array will be 2n minus 1, right? It's not, so for n elements you have to double the size and store that much, maintain that much array, and then in the array you use the formula to go to parent and child. So that we can see tomorrow, the detailed pseudocode in that language.